In this video, we're going to talk about conservative fields. So let's say we have a vector field, and this vector field assigns a vector to any given point in space. And let's say we have a certain point A, and we have a point B, and then let's draw a path connecting these 2 points. And then let's call this path C1. So of course we can evaluate a line integral along C1. So this line integral will result in some value. And then of course we can also draw another path that connects point A to point B. And then for this other path we'll call it C2. And then along C2, of course, we can also evaluate another line integral. And the question now is whether these 2 line integrals give you the same value. And their answer is that it depends on the vector field. So for some vector fields, these 2 line integrals would result in 2 different values. But then for some other special vector fields, which are called conservative fields, these 2 line integrals would give you the same value. And that's what's so special about conservative fields. So for conservative fields, it doesn't matter what path you take. So another word for this is that line integrals are path independent. So it doesn't matter what path you take. As long as your line integrals have the same starting and ending point, then they will have the same value. So if this vector field is conservative, then these 2 line integrals would give you the same value. And of course, if I draw some other path with a starting point A, and then this path could be something completely crazy, and then if it ends in point B, then because this vector field is conservative, then we will know that this line integral will be the same, will give you the same result as these 2 other line integrals. So that's what a conservative field is. A conservative field is a vector field where line integrals are path independent. So in order to make this a bit more concrete, let's do an example. So let's say we have a vector field equal to yzi plus xzj plus xyk. So I can assure you that this vector field here is conservative. So later on we'll talk more about how we can determine whether a vector field is conservative or not. But for the time being, just accept the fact that this is a conservative field. And then we're going to check that this is indeed a conservative field by doing a line integral along 2 different paths. So let's define the path C1 to be a path given by this vector value function. So this is the path that is essentially a straight line in 3D space that goes from the origin to a certain point. And let's say t will range from 0 to 1. And if that's the case, then this will define a path that goes from the origin all the way to the point 1, 1, 1. So this is the point with an xyz coordinate of 1. So this line over here is C1. And let's say we have another path, C2, and then C2 will be the same path that we worked with in the previous video. So if you remember, we actually saw this from the last video. And then t, once again, will range from 0 to 1. And then for this path, it will bend slightly at the start, and then it will eventually reach the same point. So in this curved path over here is C2. So you see, both C1 and C2 have the same starting and ending points. And since I told you that this vector field here is conservative, you would expect that the line integral along C1 and C2 to be the same. And that's exactly what we're going to check in this video. We're going to verify that that the line integrals along these 2 different paths would give you the same result. So let's do the line integral along C1 first. So we're going to use substitution. So t ranges from 0 to 1, and then we have the vector field dot dr dt, and we're integrating this in terms of t. So first of all, let's take a look at the vector field. So the vector field is just equal to this, and then along the path C1, x, y, and z will all be equal to t. So we know that the vector field, we can just substitute in t for all the x, y, z's that you see over here. So this term just becomes t squared, this also becomes t squared, and this also becomes t squared, because x, y, and z are all equal to t along the path C1. So your vector field is just going to be t squared I plus t squared j plus t squared k. And then we need to dot this with dr dt, so we just differentiate this with respect to t. So this just becomes 1, 1, and 1. So dr dt is just I plus j plus k. So we have I plus j plus k, and then dt. So taking this dot product is easy enough, so we just multiply 1 with t squared, so we have t squared. And then for the second term, we multiply 1 with t squared, so we have another t squared. And then for this third term, we multiply 1 with t squared, so we have another t squared. So this is just 3t squared. And integrating this just becomes t to the power of 3. Evaluating this from 0 to 1 is just equal to 1. So this is the value of this line integral. So now let's move on to the path C2. So now we do this line integral. And since I told you already that this vector field here is conservative, we would expect this line integral to be equal to 1 as well. And later on you will see that this is indeed the case. So once again we use substitution. T goes from 0 to 1. And then we need to write down the vector field in terms of t, and then we need to differentiate r, and then integrate this whole term with respect to t. So for the vector field, we have y, z, and along the path C2, x will be equal to t, y will be equal to t squared, and z will be equal to t to the power of 3. So yz is just t squared times t to the power of 3, so that's just t to the power of 5 in the I direction. And then for the j direction, you have x times z, so t times t to the power of 3, so that's just t to the power of 4 in the j direction. And then now you have x times y, so it's just t to the power of 3 in the k direction. And then we need to dot this with the derivative of the path with respect to t, so it just becomes I plus 2tj plus 3t squared k. So we have I plus 2tj plus 3t squared k. And then we're integrating all this with respect to t. So this dot product should be easy enough. We multiply 1 with t to the power of 5, and then we multiply 2t with t to the power of 4, so it becomes 2t to the power of 5. And then we multiply 3t squared with t to the power of 3, so that becomes 3t to the power of 5 dt. And you can just add this up, you'll see that this is just 6t to the power of 5. And integrating this, you get t to the power of 6, evaluated from 0 to 1. And of course, this is just equal to 1. And so there you have it. You can see that both of these line integrals give you the same value. So I hope this example over here gives you a bit more concrete idea of what exactly is a conservative field. So just keep in mind a conservative field is a vector field where line integrals are path independent. So as long as your line integrals have the same starting and ending point, then the line integral would give you the same value, as is the case over here.